So the PhD is entitled Enhanced Geospatial Data Analytics with Large Language Models. So in the recent years, we've seen the emergence of large language models for various tasks, and particularly for spatial information. A few years ago, these language models were only trained just to reproduce the patterns of words. For example, Melbourne is a city in Australia, which was a hard task. And now researchers have injected large amounts of data and or texts, and the language models have learned the capacity to learn the subjacent observations in this text. And this offers a very interesting framework, a unified framework between geographic information retrieval and natural language processing. But there is one limitation in the use of large language models for geospatial information is due to the distribution of the data sets. For example, people on the right side of this of the screen, you can see a cartogram which represents the distribution of the Australian population. And we can imagine that each people from Melbourne or Sydney would tend to write documents or texts on the internet that is related to their town. Let's say that I would tend to write more about Melbourne, or people would tend to write more about Sydney, but much less about the regional areas or less popular areas in Australia. And this is a limitation for the language models, because if we can prompt the language models to ask, what can you say about the center of Australia, the language model would struggle. And if we represent this knowledge on a map, potentially we can have visual problems, and this is shocking for the final user. So for this PhD, I worked at decomposing into 3 questions. So the first question is just to translate what is existing in natural language processing, and to use these tools to answer a query related to spatial information. The second research question is mainly based on these distortions that we can have in language models applied to geospatial information. So how can we evaluate these distortions? And the third research question is, knowing that we have such biases or distortions, how can we control the bias just to improve the quality of the answers after a language model? So for the first and second year, we've mainly worked on one book chapter, one conference, just a poster, and a paper which is under revision at the moment. And in terms of progression, so in the first year, I will just have a quick recap, but it's mainly about using the existing tools in natural language processing and applying it naively to a geographic information retrieval task. For the second year, I had 2 subtasks. The first one is the evaluation of the biases in the language models relatively to the spatial knowledge, and how can we mitigate the information overload in the use of large language models. For example, we can use them to answer to a complex query with a semantic matching and a spatial matching, and maybe it's too much for the language model. And I'm going to explain what I did, and just we'll have a short overview of what I expect to do for the third year. So in terms of geographic information retrieval, I just give a general overview of the scope in question answering. Spatial information is extremely rich, and it can be decomposed in different types of knowledge bases, such as texts, tables, and graphs. And not in the domain of natural language processing, it is researchers have 2 approaches to answer a question. Either they use dense retrievers, for example, Each text or table graph are represented under the form of vectors, and we calculate a similarity between the vector that represents a query and the vector that represents a potential candidate. Multiple works have been done around word embeddings at the moment with retrieval augmented generation and also with graph neural networks. On the other side, this is a second approach. Researchers tend to use to decompose a query and pass into a logic expression. For example, I want the condition A plus the condition B plus the condition C, and this leads to the creation of queries in SQL, Sparkle, and Ceph. The approach I want to follow is RAG, retrieval augmented generation, mainly due to its capacity to generalize to a vast amount of questions. So this is what I did in the first year, is to find the origin behind each place name, who is behind Batman Street in Melbourne. To do so, I mainly wanted to work on knowledge graphs because they are the most unambiguous form of knowledge bases. And the idea is to have chunks of information and to find the right candidate. Is it Batman, the superhero, that is linked to a spatial location? Or this is a Batman, which is a job? Or is it another person, which is John Batman? So we used, reused this query, who is the Batman Street, most likely named after in Melbourne, in Australia. And we used a series of different modules, a searcher, indexer, retriever, and a generator. First, we extract the information from the internet, from DBpedia, which is a knowledge base. We chunked the information and we created a vector. And at the end, we calculated the similarity between our query and each of the vectors that is linked to a chunk of knowledge base. And the idea is to rank the different chunks. We also fine-tune the model to better understand spatial information. In terms of results, what we had is here we have 15 streets in Melbourne, and we just plotted here at the rank 1 to 10 if the answers are related to Australia and more specifically to Victoria. And we can see that the state-of-the-art models in natural language processing struggle to think spatially, because here we have a huge heterogeneity in terms of information. When we fine-tune the models, we have a better homogeneity in terms of distribution. That means that the candidates, the top 10 candidates, are more related to Australia or Victoria, but it's still not enough. So for the research question we raised in the beginning, can we use the language models just to automate the process of finding an answer to a certain question? The answer is yes, we can use large language models to do the process, but we still have limitations. The first limitation is a strong bias that tends to privilege the semantic understanding rather than the spatial understanding. The second point is that we can fine-tune the maximum, but the model still struggles to understand the spatial component. And the third limitation is that we use language models as the core element of our retrieval systems, but do this language model really understand space? And this is what we wanted to study in the second year, is to find which are the distortions or biases in these language models. So distortions can be seen as a difference between a ground truth and the concept, the representation of a model that a model can have. So what is particular with spatial information is that everything is structured with gazetteers. For example, we know what is content into which element, we know what is adjacent to which other elements. But the main problem is that language models have been trained on data sets where people like you or me can write, and we have a certain subjectivity or sense of place. For example, I come from Europe, and I've always thought that New York is a bit at the north of Madrid, because Melbourne, New York has more blizzards, and Madrid is more related to Spain with heat, but it's wrong because they share the same latitude actually. And this is, let's say, a cognitive bias that we can have in the models. So I wanted to study these distortions, and I focused on Greater Melbourne with all the suburbs across Greater Melbourne. And I prompted the model which suburbs are immediately adjacent to this given suburb. And I could create lists of adjacency for different language models. And I compared with a gazetteer as a reference. And I studied precision, recall, symmetry, and also centrality. So I'm going to explain a bit more after. So just with after we prompt the models, this is qualitatively this type of representation that we can have in terms of adjacency with true positive edges. That means that the models perfectly detects the right edges. False negatives, that means that the model detects wrong connections. False negatives, that means that the model couldn't detect the right connection. And false positive, that means that the model has fabricated the edges. On the left side, with a small large language model, Llama with 13 billion, we can see that the model in blue has created lots of additional edges, particularly here in the Bay, Phillip Bay. And that means that the model doesn't have any understanding of the physical property of the world. And the model can cross over the sea. And we can see lots of missing edges. When we prompted GPT-4o Mini, the problem is less visible, but it's still existing. And we have still this problem here with bicolored edges. That means that one suburb really detects the right connection, but from the other side, we have a problem where the neighbor couldn't detect the right edge. So in terms of quantitative analysis, we have different models. Colbert, which is a very small model with 100 million parameters, and we studied up to 70 billion parameters, and potentially a bit more with GPT-4 or Mini. What we could see is that precision is extremely low across all the models, less than 60%. Recall is equally low, and in terms of symmetry, which is normally we expect, if language models are perfect knowledge bases, we expect that knowing that A knows that its neighbor is B, we expect that B knows that its neighbor is A, but the score of symmetry is extremely low, which is a sign of unbalanced or biased models for spatial information. We can go a bit deeper by decomposing, not sitting at the graph level, but at the level of each node. And we can see that precision is low for the different nodes in across Greater Melbourne. So this is, for example, for Colbert, Mixtra, and Llama 30 billion. And precision is low because models tend to write a lot. For example, I asked, what is the neighbor of Melbourne? And we can have Fitzroy, we can have Carlton, etc. But the model can tend to hallucinate a lot, saying Melbourne Southwest, Melbourne Northwest, and this lowers the precision. But this verbal strategy is a good thing also for the recall. And that is why Mixtra has an extremely high recall due to this capacity to generate lots of information. And in terms of symmetry, this is another problem that we observed, as symmetry is poorly respected at this fine-grained level, which is the suburb level. We studied the autocorrelation. That means, do we really have, let's say, areas where we have more lower scores? And the answer is not. With the spatial autocorrelation, it's we detected that there is no autocorrelation. That means that all these anomalies are extremely punctual, like exceptions in the language model. So there is no regional pattern. And this is an interesting property for retrieval systems. It's the centrality. That means if I ask a question related to Melbourne, what is the capacity? What is the discriminative capacity, or what is the capacity to gather all the information around the key element, which is Melbourne? We can see that Colbert has a high centrality. That means that lots of information would tend to point at Melbourne, and that means I would retrieve more, potentially more information. On the other side, Mixtra and Llama, it's quite confused because everything seems to point to at anything else. So it would be a loss in terms of quality of information that we can retrieve. So in terms of analysis or evaluation, so we had this question: how can we evaluate spatial distortions in language models? So the answer that is via probing. We probe the language models by analyzing the outputs, and we could see that we have too much variance in comparison with gazetteers. We have a sort of propriety bias that is extremely present in the language models, and bias is not necessarily negative for us. If we focus on the origin of the streets in Melbourne, it is a positive bias, because if we use, I just have a recap, Colbert, a small model, all the information would be better clustered around Melbourne. So finally, we could see that language models have struggles with spatial information, and we could see that also in the first year they struggle with the semantic understanding. So how can we deal both with semantic and spatial understanding at the same time? The partial answer is to mitigate information overload. So we picked almost exactly the same framework, but I didn't want to create a new framework. What I did is that we had a complex query, which is finding the origin of place names, and I decomposed into two different tasks. First, the two different conditions. I want that the answer perfectly matches with an origin, and the second condition is that I want that the answer matches with the location. So there are two conditions, and I wanted to simulate this type of probability, having the condition 1 and the condition number 2. And I simulated this within the language, within our framework. What is particular here is that I used exactly the same fine-tuned ranker here, but I created these two views, one view just to simulate one probability, and the second view to simulate the second probability. And also, just to mitigate information overload, I also wanted to extract. We had as an input knowledge graph, which contains lots of information, but I just wanted to calculate the probability on the spatial relevance. I wanted to extract only a sub-knowledge graph that is only spatial. That means that only the triples are related to spatial information. As an illustration, so this is a knowledge graph I can have as an input from DBpedia, where, for example, John Batman lived in Melbourne. John Batman has a job, which is Grazier, and John Batman, and which has this type of information and long texts. And this type of information can be a bit too much for language models. That is why I used in the rewriter, I wanted to extract the interesting names: British colony of New South Wales, Batman, let's say places, organizations, and people. And I prompted a language model just to execute a triplet extraction with as an open information extraction task, just to extract a sub knowledge graph only related to spatial information. And at the end, I used RDF mapping language just to create my knowledge graph under specific format. As a quick reminder, this is what we had at the end of the first year. So this type of distribution for 15 places, and we had a lot of heterogeneity in terms of spatial matching. With this framework and exactly with the exact fine-tuned models, but reorganizing a bit differently, we improved the score because we have a more homogeneous recommendation for the top 10 items. That means that our multi-view representation has increased this alignment to have spatially more related results. We just conducted a certain ablation study. By wondering, is it important or useful to write our rewriter and to extract a spatial knowledge graph? The answer is potentially not. It decreases a bit in terms of results just after the ranker, but it's in my opinion, it's an extremely expensive step because we use a large language model and it took a lot of time, and we don't have much more in terms of improvement. We lose a bit if we remove this module. In terms of analysis after the generator, so we had a ranker to rank the different candidates and the generator to find the final answer to the question. We didn't find any better. We found a better results after the ranker, but not after the generator. And I think that we reached the limits of we reached a limit of how much a language model should how far can language model should behave to take decisions, because we have a very subjective question, which is finding the origin of a place name, but the language model is not the suitable model to subjectively think. So in terms of controlling the spatial bias, which is the third research question, we can partially do this by creating a strategy in our pipeline by dividing, having different conditions that we analyze in parallel. But we also faced a limitation here in terms of results, is that we wanted to answer to a factoid question answering, who is exactly behind an origin, versus a recommendation where we want to have not necessarily the right answer, but where we want to have potential relevant candidates. So this is a limitation of our work, and the second limitation that we are facing is how can we put constraints in the model? If I really want to find candidates related to Melbourne, should we try to work with language models and to put constraints on these models? And this is what we are working on for the for the third year is that we have, for example, a query. I just extract a small piece of information of the query. I want, let's say, restaurants in the east of Melbourne. And we were working on the knowledge graph, for example, DBpedia. And at the moment, we just injected this knowledge graph and worked as if it was a plain text into a language model. But we are losing lots of meaningful information that are the spatial triplets. And in these spatial triplets, we can have polygon, parentheses, and this series of numbers. We can have points, etc. And this is not properly understood by language models. So the idea for the year 3 is to align the text with better understanding or better activation of which parts of the knowledge graph we want to study. And the idea is to link this spatial information to sorts of hypernodes just to augment the model and to match, to align these chunks of text with these hypernodes and to better extract subknowledge graphs for our retrieval. In terms of illustration, this is what I would like to do is, if I have an expression such as southern coast of Australia, I want to activate just this hypernodes, and this would be meaningful to link with an existing knowledge graph, just to have potentially better answers. So as a conclusion, we have 3 milestones. In the first year, I just wanted to use naively what we had in natural language processing and to apply to geographic information retrieval. We did this. Second year, it was more focused on maybe refining the knowledge graphs. Finally, I transformed a bit. I wanted to work more on the evaluation of the biases and to redefine the strategy in the use of large language models. So finally, the creation of the knowledge graph and the refinement finally are just one small step in the final pipeline. And what I presented in the COC for the milestone number 3 was the development of a ranker module for better spatial similarities. So we are in this track to in the aim of improving the use of large language models to perform question answering with spatial information. So I thank you for your attention and hope you have many questions.